Okay, in this video we'll look at two more examples requiring the chain rule, and the first one is we have to differentiate y equals the square root of x squared minus 4x minus 5. So hopefully you recognize that we have composite functions here. We have a trapped quadratic and a square root, and instead of a square root, of course, we're going to write that as a power of a half, so we can differentiate using our power rule as part of our chain rule here. First link in our chain, I guess, and let's write our trapped function in a separate color. Yellow is as good as any here. Nice and bright. So if we're differentiating this function, well, it requires two chains. First chain is going to be the derivative of the outside function, which is the square root or power of a half function. So it comes down in front. And I subtract, I should say the power of a half comes down in front, and then I subtract 1 from that power of a half. So we've successfully differentiated the outside function. And remember, the common mistake is to make sure you trap the trapped function in that outer derivative still before you move on to the second and final link in this chain. So now the final link in the chain is maybe in a separate step, as we now have to multiply by the derivative of the inside function. And if you can just write down the derivative without having to do the differential notation here, that's fine as well. So this is going to be the derivative of x squared minus 4x minus 5. So that's all going to be 2x minus 4. So I think I'll just wipe that clean and say multiply that by the derivative of the inside in yellow, which I guess will be 2x minus 4. And keep in mind, that's a terrible way of writing that. You've got to use some brackets on that because that whole binomial is multiplied by all this other stuff. So we don't always have to clean up our derivatives, but if we ever have to actually use this to find a certain slope, or even to get a slope sometimes, a little bit of cleaning up is not too big of a deal. So maybe we should do that. And I'm noticing I can take that half and multiply it by 2x minus 4. Or I can factor a 2 out of that and times it by a half, whatever makes more sense to you. Either way, you're going to get x minus 2 when you multiply those two terms together. So x minus 2. And the other thing I'm going to do is rewrite this expression. I get rid of the negative power, move it to the bottom, and I'm actually going to go one more step further. I'm going to write it back as a square root again. So this is a square root on the bottom, and of course that x squared minus 4x minus 5 is still trapped. Now the denominator in that square root. Okay, in our second example, we have the reciprocal of 8 minus x cubed. So hopefully you recognize you have 8 minus x cubed trapped in the basic reciprocal function. So we have to use the chain rule. So I think before we do that, we're going to write this another way. I'm going to say, you know what, since this is the reciprocal of 8 minus x cubed, I can use a -1 exponent. And maybe that's allows you to see that, oh yeah, I do have a composite function here. I have something trapped in the basic reciprocal, because remember, anything to the power of -1 is just a reciprocal. So now we can go ahead and differentiate, and keep in mind we have an 8 minus x cubed trapped in our basic reciprocal function that we're going to differentiate using a -1 power, and so we can use our power rule. So our derivative is going to be differentiate, and I'll write -1, even though you don't need the 1, the negative symbol's enough. So we'll differentiate the outer function first. -1 comes down in the front, subtract 1, and maybe I'll write this out again in yellow. Don't forget to trap your 8 minus x cubed. And now we can go ahead and move on to the derivative of the trapped piece, that 8 minus x cubed, which I will write out in a separate step. That's probably not necessary. As long as you can differentiate it fairly quickly, you can write it down. Okay, so, and maybe I'll write that out as an entire different step this time instead of just erasing it, if that threw you off last time. So this is a minus in front of 8 minus x cubed to the power of -2, and then we'll multiply this by the derivative of that inside function. The derivative of 8 is 0, and then minus the derivative of x cubed, so it's going to be a -3x squared. So let's take a little bit of time just to clean that up a little bit and at least get rid of those two negatives, which would definitely sharpen up our work if we needed to use this derivative for anything. And so it's going to be a positive 3x squared, and then I'm moving that power down to the bottom, get away from not just negative coefficients, of course, and two negatives there, but also to get rid of that negative power. So this 8 minus x cubed can go to the bottom, and now it's to the power of positive 2. And please don't expand out the bottom. I mean, it's not wrong to do it, but it's usually not something you want to do, because remember, you'd want to be aware of what potentially can make your denominator equal to 0. And not that we want to delve into this too much, but if you set that equal to 0, or even just look at this x cubed, substituting a positive 2 in there would actually give you a denominator of 0, meaning that you can't find the tangent slope at x equals 2. And once again, the numerator is going to tell you where your stationary points are. Whatever can make the top here equal to 0, which looks like x equals 0, would make 3x squared equal to 0. That's where a stationary point is going to be. So if you have your derivative, just to remind you, don't get too focused on the chain rule that you forget what your derivative is for. It can allow you to find the tangent slope almost anywhere, because now once you see these denominators, there's going to be a few x values that give you division by 0, meaning that you can't find the tangent slope there. And also, if you have your derivative, you can look for specific slopes, tangent slopes as well.